Okay everyone, we are working in chapter 18 now. This is number 18.18, so it's write the solubility product constant, which is KSP, expressions for each of the following compounds. So what we first need to do is write out the reaction for each of these compounds when it dissociates in water, or because they're soluble. So they're just going to break up into their ions. So we're going to be using the periodic table a ton for this. Calcium is in the second row of the periodic table, so we know that when it becomes an ion, it has a positive 2 charge. And, sorry, not the second row, the second column. And so since it has a positive charge, and there's a subscript of 2 here, then that would mean that, there's a subscript of 2 here and 1 here, then that would mean that what is that, fluorine? Fluorine is in the, okay, let's just redo that.
Okay.
Okay, we're working in chapter 18. This is number 18.18, and it says write the KSP, which is the solubility product constant, expressions for each of the following compounds. And I have them written out here. Our first step will be to write out the reaction that happens when these solid compounds break up into their ions when they become dissolved. So we're going to use the periodic table a lot. The calcium is in the second column of the periodic table, so we know that has a +2 charge. Fluorine is in the second to the last column over here, so we know that it has a -1 charge. So we're going to write that out like that. And then there's also 2 fluorines, so we're going to make that the coefficient for fluorine, so that it's all balanced. So then what you do is to write the solubility rule. You're just going to write KSP equals, and it's just going to be the product of the 2 raised to their coefficients. So super easy. Alright, so I'm just going to go through them. I'm going to go pretty fast because there's a lot. So silver and carbonate, yeah. We know that carbonate has a -2 charge, so that means that if we want to cross multiply or whatever, this has a -2 and this has, so this must have also a 2 charge. Just a 1 charge on the silver because that has a 2 charge. So it's going to be silver plus and carbonate 2 minus, and then since there's 2 silvers, we're going to put that as the coefficient. So this is the easy part, where we just write them out so that they're products of each other raised to their coefficients. Now for this one, we have lead and sulfate, so it's going to be Pb lead 2 and sulfate. We know sulfate has a -2 charge, and they're in a 1-to-1 ratio, so that's how we know that this is lead 2 instead of one of the other forms of lead. Which is what I was trying to say up here, but I just didn't say it that nicely. And both of them have 1 coefficient, so we just don't show those. They're just implied. Moving along, we have OH, which we know has a -1 charge, and since there's 3 of them, then that must mean that this is iron 3. And there's 3 of them, so coefficient. Don't forget to raise it to the power. Here, iodine has a +1, or has a -1 charge. And since there's 2 of them here, then you know that this must be lead 2. keep on going. Sorry, this is messy. Trying to write it fast. And then can do the same thing. OH is a -1 charge, so this must mean, since there's 2 of them, that this is copper 2. So sometimes those transition metals can be tricky, but all you have to do is remember that to look at the ratio that they're in, and then that will determine, as long as you know one of them, the charge of one of them, then you can figure out the charge of the other looking at the ratio. So. All right, that is all of it.
18.20. In water, the solubility of lead chloride is 0.016 molar. Use this information to calculate the value of the KSP for lead chloride. All right, so we know that lead chloride has a solubility of 0.016. And we'll want to keep that in mind just a little bit. Right now what we're going to do is we're going to write out this equation when it dissolves in water. So that is just Pb2 plus 2Cl minus. And again, Jacqueline kind of went over this in the problem before, but we know that these subscripts just kind of, what is it? I don't know, switch over. And so anyway, so we know that the charge of Pb is going to be 2 plus, because it switches over, and then the chlorine is going to be just minus, but there's 2 of them, so we put the 2 right there. And you can get all this information, you can figure this out if you don't understand from looking at the periodic table of elements. Again, chlorine is in the second to right. It's just to the left of the noble gases, so we know it has a -1 charge and so forth. So anyways, so you should be pretty good about figuring that out. Next thing that we're going to do is we're going to write out the KSP law. So KSP is equal to, we got it's just this right here raised to the exponents that they have. So, or raised to the coefficients?
Yes.
The coefficients that we have, excuse me. So Pb 2 plus, but there's only just 1, so raised to the power of 1. And then chlorine minus, but raised to the power of 2 because we've got 2. So anyways, so that's what we have. And then what we're going to do is we're just going to plug in the information that we know. And they told us in the problem that the solubility of lead chlorine is 0.016 molar. Use this information to find that KSP. So that is what we're going to do. And we're just going to plug in the information. At equilibrium, the lead 2 plus is going to be 0.016 concentration. And we know that because there's just 1 lead. We're dealing with 1 lead. Is that compound? So that just equals 0.16 when it dissociates. But because there's 2 chlorines here, this concentration doubles for chlorine. So what I'm trying to say really is we have 0.016 for the lead right there, and then we're going to have 0.032 for the chlorine. And that's just because when this dissociates, we've got 2 chlorines, and so we have to account for that. And then, so plugging this into the equilibrium law, we're going to square that right there. And from here on out, it's just algebra, and you get 1.6 times 10 to the -5 for the KSP. That's what that equals. So that's the answer right there. And that's how you do it.
22. Barium sulfate is so insoluble that it can be swallowed without significant danger, even though barium ions is toxic. At 25 degrees Celsius, 1 liter of water dissolves only 0.00245 grams of barium sulfate. Calculate the molar solubility and KSP for barium sulfate. So, this is just like the one we just did, except for that they just add an extra step there for us. So this is barium sulfate. We have to figure out what it becomes when it dissociates. They gave us a clue in the problem and said that it was going to be barium 2+, which we could have found out anyways because we know that sulfate ions have a 2+ charge, and since it's in a 1-to-1 ratio, barium must also have a 2+ charge. But thankfully they gave us it in the problem. So we know that that's about how it dissociates. This is solid, sorry. So our KSP law then is going to be barium ions times our concentration of sulfate ions. And the reason KSPs are just the products of the product of the products.
Oh no, this is dying on us.
Right now. Alright, sorry about that pause. Our camera died. But we got it going again. So back to 18.22. Here we are. So we already wrote out the equation and the KSP. I was explaining that the reason that KSP is only the product of the products and the reactants aren't in there is because the reactants are always solid, since it's a solid dissolving into ions, and solid is a pure substance, and pure substances don't go into equilibrium laws. So KSP is really just like a special type of equilibrium law, just like the Ka is a special type of equilibrium law. It's the same type of thing. So here we are with our KSP, and what they gave us was that 0.00245 grams dissolves in 1 liter of water. So we need to get our concentration from that. So we're just going to use some good old dimensional analysis. I think I'm going to do it over here. We have 0.00245 grams, and we're going to multiply that and get moles, so it's going to be 1 mole of barium sulfate, and then using the periodic table, if you figure out the molar mass, it's 233.3906 grams of barium sulfate. It's pretty large. So that gives us our moles, which we end up with 1.05 times 10 to the -5 moles of barium sulfate, and they already told us that that was how many grams in 1 liter. So this is moles in 1 liter, so this is really just our molarity. So that's the molarity. Since barium sulfate dissociates in a 1-to-1 to 1-to-1 ratio, so there's 1 mole of this dissociates into 1 mole of barium ions and 1 mole of sulfate ions, then we can just plug that right into there. And when we do that, then I'm just going to put an arrow because I don't feel like writing it out twice, but we're going to plug that into here and here, and then multiply that out, and we end up with KSP. I'll just show that. KSP equals 1.10 times 10 to the -10. Oh, 10. And that is the answer.
18.24. I'm just going to give you guys a heads up. There was some discrepancy between values that we calculated and the answer in the back of the book. So we'll just explain this problem conceptually. And I'll start off by reading it.
A student evaporated 100 milliliters of a saturated BAF2 solution and found the solid BAF2. She recovered weighed 0.132 grams. From this data, calculate the KSP for the BAF2. All right, so what we're going to do, what we did first is we just wrote out this equation. BAF2, what it dissociates into. We've got our two ions, fluorine and barium, and you can figure this out looking at the periodic table. Barium is going to be an ion with a +2 charge, fluorine has a -1 charge. There's 2 fluorines. So we know that our KSP is just going to be barium 2+ raised to the 1 power times fluorine negative raised to the 2 power. So what we want to do is they told us that they recovered 0.132 grams of BAF2 from 100 milliliter solution. So we're going to use that information to calculate these 2 concentrations. So we'll start off straightforward, 100 milliliters, doing dimensional analysis. That's equivalent to 0.1 liters. And then also they told us that we had 0.132 grams recovered of BAF2. And so what you're going to want to do is you're going to want to convert this grams into moles using the molar mass. So what you would have is molar mass of BAF2 over 1 mole of BAF2. And then this equation is a 1:1:2. And so when you work this out, you know that you're going to have 1 mole BAF2 is equal to 1 mole of BA. And then because this is a fluorine has 2 moles right there, when you're doing your dimensional analysis to get moles, both of these concentrations, you just put 2 for the fluorine. And so anyway, so then you'll have moles, which is what you want. And because they gave us the milliliters and liters, you divide that by 0.1 liters, and you'll have your concentration for each of these compounds, and just be able to do algebra and work it out. So I'm not sure where our numbers went, where they diverged from the book's numbers, but anyways, they didn't add up, so we don't have an exact answer, but overall, they give us grams, we want moles, and they give us liters, so we're going to divide our moles by liters to get a molar concentration, which we are plugging into this equation, the KSP. That sounds fine.